The law of conservation of momentum, 6.0, simply states the total momentum in the universe is constant. Now, if we take the universe and say, this is the universe, we chop off a little part of that universe, we can define that as our system. So a system is a piece of the universe, which means we can also write the law of conservation of momentum as the total momentum in a system is constant. The total momentum of a system remains constant. Here is the deal. The rule is it's always true. There are no exceptions. It turns out there are some other conservation laws that are not quite true. There are some exceptions. For momentum, there are none. Now, this formula, the total momentum of the universe remains constant, is simply put is the initial momentum equals the momentum at any instant in time. So if we break off a part of the universe for our system and we figure out how much momentum is in there, that total amount of momentum is going to stay the same. If it appears not to remain the same, then we have not properly defined our system. Extremely important. We might say that there's a little cart that is at rest, and then we look later and it's moving. Its momentum changed. There is a delta P that is not equal to 0. If the initial momentum was 0, but later it doesn't have 0, wait a minute, the momentum has changed. It's true, the momentum of the object hasn't changed, but that object is part of a system. And if we say that that total momentum of the system hasn't changed, we're incorrect. We have left something out of our system. It's not a trick. It's the truth. So this is the most basic statement of the law of conservation of momentum. The initial momentum equals the momentum at any instant in time. Now, it could be that there are a number of particles involved in our system. 1 or 2 or 3 or 4 or 10. So what we could say is the sum of the initial momentum is going to equal the sum of the momentum at any instant in time. Which means we could have P01 and P02 plus P03 plus ... will equal the sum of the momentum afterward. P1 prime plus P2 prime plus P3 prime. Now this designation prime means after. So if we have P1 prime, that means the momentum of object 1 afterward, whereas P01 is the initial momentum of object 1. Now we can have 10 particles beforehand and 6 particles afterward. We could have 10 and 10. We could have 1 and we can have 1,000. One thing could break into 1,000 pieces, but the momentum of those 1,000 pieces will be equal to the momentum of the one that it came from. So the most general statement is the total momentum of the system is constant. That's P0 equals P. But there may be some number of particles beforehand and a number of particles afterward, and we have to add up the befores and the afters. The number of particles does not need to agree before and afterward, but it must include all the particles that were originally in the system. How do we go from 10 particles to 6 particles? Well, some could have stuck together. Ten equals 10. Well, that's pretty obvious. There is maybe no change. 10 could go to 1,000. That could be an explosion or some kind of division. And so forth. But that is the fundamental idea of the law of conservation of momentum. It is always, always true. And this is why I oftentimes think of the conservation of linear momentum as the king of all the conservation laws. Or queen. Because it is always, 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 always true. And that is the law of conservation of momentum. In the following episodes, we're going to look at installments. We're going to look at different types, different examples, and the applications that come out of those.